allow 3 sites for bonding while maintaining just this lone pair on top that will stay there.
I already know what the pairs are.
Yeah, so what's that going to be?
There's going to be 3 loads. There's 3 load atoms. It's 2 lone pairs.
Okay, so remember a pair includes the 2,
Pairs.
so we're going to have exactly what he just said. So around this nitrogen, we're going to have 3 bonded atoms, and you're going to see that illustrated up here, right? Because there's 3 hydrogens bonded to it, and as he pointed out, there's 1 lone pair. Be careful, it's really easy to say 2 lone pair because you're counting 2 electrons, but remember a pair means 2, so you only have 1 pair, like 1 pair of shoes means 2, here's 1 pair of electrons. So the reason it's considered a type of tetrahedral is because it does have 3 atoms and 1 lone pair for a total of 4, which tetra means 4. But we give it this unique name of trigonal because only 3 of those are actual atoms. Now, you saw earlier trigonal planar, and trigonal planar was when 3 things bonded and they stayed flat, like on a plane, on a flat plane. Here, though, these 3 things bond, and instead of laying flat, like you might see in a trigonal planar, you're going to see a little bit of a lift. And the reason for that lift is the lone pair on top is pushing everything down. So in fact, you're going to see almost like a pyramid shape. Whereas trigonal planar, the one we looked at earlier, would lay flat on its surface. So this is what you're going to see, and of course you're going to see up here that we should have 2 dots illustrating the lone pair that push this down and make this kind of a pyramid shape that you see. So let's do a couple quick examples. We have BH3. We want to draw the Lewis structure and decide whether this, or just determine what shape this will take. So if we look at BH3, then we know B is going to be your central atom, surrounded by 3 H's. Now boron has 3 valence electrons, so it's going to make 3 bonds to the 3 hydrogens. So how many bonded atoms are there? 3. How many lone pair? None, right? So here we have 3 bonded atoms and 0 lone pair. If you look at the chart you just filled out above, only one shape has 3 bonded things. So what's the prefix going to probably be if it's 3?
Trigonal.
Tri, right? Trigonal. And 0 lone pair means it stays flat. It doesn't lift it up like a pyramid. So we're going to have a trigonal planar shape. And again, that's what you see here. This flat surface that it can sit on, but 3 bonded atoms. CO2. Now this is a classic example, but it does get a little tricky if you're not careful. Carbon dioxide, as you all know, CO2 is made up of 1 carbon, which has 4 valence electrons and is in the middle, and 2 oxygens. Now, the oxygens have 6 valence electrons, and they can make themselves each 2 bonds, right? And we have 2 of them. So what's going to happen here is what's called a double bond. Well, let's see what happens when we finalize this. Now, whenever we count lone pairs, we only count the ones around the central atom. So these are not going to be considered lone pairs here. Where focus is around just the center atom, the one in the middle, the one who's the focus of attention. And then, of course, this oxygen has 6 valence electrons as well and can make 2 bonds. So you're going to see 2 bonds occur here. Now, it looks a little messy, but what you actually end up getting is a carbon that has 2 bonds connecting it to this O and 2 bonds connecting it to this O. Now, these lone pairs on the oxygen do remain on both, But we don't count those as lone pairs because what we want to count is the central atom. How many atoms, and this is another tricky question, how many atoms are bonded to this carbon? The answer is just 2. Even though they're double bonds, remember their steps, there's still just 2 atoms bonded, 2 oxygens, right? So what you can see already is this shape that it's going to take is just a straight line. And we call that linear, and here you see a few different versions. Now this one we know is specifically carbon dioxide because again it is showing those double bonds, but keep in mind that even though it's a double bond, this is still only 1 atom bonded to the central atom, a second atom bonded to the central atom, so this is 2 bonded atoms and 0 lone pairs. And refer to the chart above and you know that that will be the case for anything that is linear. Next, we want to talk about polarity. And this idea is pretty simple, especially whenever you think of it in terms of the way I'm going to describe it to you today. Polarity, think of the north and south pole like the world or like a magnet. We have 2 different ends. Now this occurs when the electrons involved are not shared equally. So if you recall, this unit over covalent bonding is all around based around the idea that sharing is caring. Sharing is covalent. So electrons are being shared. So if we have any electrons, as they're shared between the atoms, you sometimes see that they're shared equally, or maybe one of them kind of hogs them a little bit more than the other. This is going to result in a change in polarity. Or think of it as a pool. Polarity, think of it as a pool. This is caused by a difference in electronegativity values. If you recall what electronegativity is, it's the desire an atom has for an electron, or for electrons in general. How much does it want to take electrons? Now, determining polarity would depend on 2 things. Are the atoms different, and will they pull the electrons differently? Do they have different electronegativities? Or the presence of lone pairs. The instant you see a lone pair, it's automatically polar because, as you know, lone pairs push everything. So think of this as a tug of war game, right? 2 teams, 1 rope, 1 midline. You're trying to see which way it skews to. Who's the stronger team that could take more of that rope? So you're going to look at these pictures and ask yourself, if they were to compete in a competition of tug of war, would it be a tie? Or would there be a clear winner of someone pulling it away from the other group? Now, if we look at this, you can see hydrogen is sharing electrons with hydrogen. Think of it as 2 twins, or 2 things that are equal in strength, 2 teams that have the exact same strength. And whenever we think about strength, the strength of these atoms, we're referring really to their electronegativity. So whenever we refer to strength, think of the electronegativity. How much do they desire electrons? Well, hydrogen versus hydrogen, who's going to win, or will it be a tie? Well, because of the same element with the same strength, the same electronegativity, there's going to be a deadlock, it's tie. It's going to be even, right? There's going to be no movement, no poles, no positive and negative end created. So we call it, when there's no pull, think of that tug of war where both teams are just stuck there. No one's moving. It's a tie. There's no pull, so we call this non-polar. However, in this example over here, you can see we have not H versus H, but now H versus Cl. Even if you don't know what their electronegativity values are specifically, you know that their electronegativity values are not the same. So one of these is going to be a winner. If hydrogen and chlorine try to share electrons, one of these is going to take over more. In this case, chlorine has the greater electronegativity, so it's going to have a stronger grasp of those electrons. Think of that tug of war competition. This is the team that's going to be winning and pulling the rope towards it. Poor little hydrogen doesn't have a chance against chlorine. So you're going to see the charge moves this way, creating one end that's slightly positive and one end that's slightly negative. And those are the north and south poles that we refer to. Because there is pull, there's not an equal sharing, one team is losing, this pull we call a polar bond. Now, when it comes down to non-polar molecules, things to keep in mind, the atoms all pull equally and balance each other out. The main reason they pull equally is due to the fact that they're all the exact same element. If you're boron here in the middle and you have 3 fluorines pulling you in 3 different directions, because they're all fluorines, equal strength, because they pull in opposite directions, you're stuck. Boron is not moving here in the middle. There's no pull. Just like we saw when the 2 hydrogens competed. Their strengths are equal, there's no movement. No pull, no movement, means non-polar. Polar, on the other hand, is whenever there is movement. Just like we saw H with Cl, clearly Cl is winning. There's a pull, there's movement. That means there's a positive and negative end that forms, giving us these 2 poles. The reason is these electrons are pulled unequally, you will see movement. Or the other reason may be they're simply lone pairs. Water is polar, and as I said, you need to know certain things about water always. And one of those things is water has a shape that is called bent, and its structure is polar. The reason is these lone pairs up here push everything down, so there is movement. There is not this equal distribution of electrons, and things are not shared. So polar versus non-polar all has to deal with how these electrons are shared. Therefore, you're going to see that polar molecules have an asymmetrical shape, meaning there's a different element somewhere, or lone pairs somewhere, or asymmetrical atoms, meaning it's not all the same atoms surrounding the central atom. Here we have 3 chlorines but 1 hydrogen. This is not a symmetrical shape. The pull is going to be different and there will be polarity, as you can see. The net dipole moment refers just to the movement of those electrons and the overall charge. So that concludes this video on molecular geometry and polarity. Thanks for watching. I'll talk to you soon.